in California, so it's bright and early here in California. San Diego is 7 a.m. So hopefully everyone is doing okay. So like Danny say, I have been working in cybersecurity for quite a while now. The reason that I got the job is really because of my knowledge of cryptography. I have done a thesis, my master thesis is in cryptography, and especially in the substitution boxes of the DEA system. So it is really important. Like we do cryptography actually every day. Gmail, I think they encrypt like 95% of your email. You don't even know about it behind it. And there's a lot of mathematics behind the cryptography that you don't notice. And you will need to have extensive math background, probability theory, a lot of like ring and group theories, those kind of mathematics to really truly understand cryptography. Nowadays is usually a lot of computer science as well. You can see the complexity of it, that you cannot really not doing it by hand. So that's why, a lot of time cryptography is really under computer science department, or sometimes it's mathematics, or sometimes it's a joint courses in the university that student can study under. So you will need both. You need the mathematical background, and you also need the computer science, to help you to implement some of this really complicated crypto system. So the textbook that I'm using, the one that I use is like called Cryptography and Theory and Practice. This is the 3rd edition. There is a 4th edition, is already out, a newer edition, so to speak, but they are pretty much the same. I don't see a lot of things. It's different, except, they updated it, and then they talked a little bit about post-quantum cryptography, which we will talk about it on the 3rd day, towards the end. So now, without telling you a lot about like the detail, what do you think about cryptography is about? So cryptography is actually a way to provide, you and I going to communicate, but we don't want other people to know. So we want to communicate not only secretly, but sometimes securely. I want to make sure that my message to you is not going to known by someone else. In cryptography, we usually have a, kind of like a nickname. We say Alice and Bob. They try to communicate with each other, and then we have a adversary called Eve, and going to eavesdrop on you guys. So she might be stealing some of the information, stealing some of the, try to hear what you guys talk about. We don't want to do that. We want to make sure that Alice and Bob can communicate, secretly and securely, and their message will not be interrupted, or not interrupted, but their message will be for sure that nobody can see it. So that's why that we want to be what do you call it, like encrypt the message, or kind of like scramble up the message, so even other people intercept it, you won't know what we are talking about. And a lot of the time that this kind of communication is really used, codes and cipher, and you probably even heard about it, during World War II. We used it extensively during the war. That's how they were actually thinking about that. By Cipher, the Enigma Machine, we shortened the war like for so many years. So that is like really good thing. And that's pretty much how the cryptography or crypto analysis is born, because we were intercepting, enemies, Germans, messages, and then we try to decipher it. So that's the background behind the cryptography. Now, beside World War II, this is actually a very, very old art. So it can probably use like about 1,000 years ago. So one of the things that is different than cryptography, because technology, ethnography, that is like a little bit different than cryptography. Cryptography is like really scrambling the message. Hopefully, nobody will read it. Nobody will know what is about if they do intercept it. Steganography is actually hiding the message, which is very, very early form of you can't say cryptography, but sometimes we still use it today. So for example, in the ancient time, there was, I don't know whether it's true or not, but we do have history like record about people actually shaving their head, and then they will like tattoo the message on their skull, and then they will let the hair grow out. And then once they deliver the message and go to whoever intended to receive the message, and they will shave their head, and then the message will appear. So that's one of the rumor that, you know, when you read some of the history, it might come up. And another one that is really cool that I bet some of you guys have perhaps, you know, already experienced it is the invisible ink. You write it, right? I don't remember the chemical behind it, but you write in a piece of paper, it's invisible for anyone, but until you squeeze the lemon on it, and then the message appears. So that's also is steganography, not cryptography. It's hiding the message. And in the more modern time, you can talk about, like, there is a way that you can hide a bit of information, some bit of information in a picture or in an MP3 file, because changing a small bit of it is not going to be affecting the picture or the music. So that's how people can hide in some of the information in plain sight, so to speak. So that's just one form of it, is a way to hide message. But now we are actually talking about not just hiding the message, but we actually encoding the message. We're sending it in code, right? If and the message has to be scrambled and nonsense if people intercept it. So not sure how to pronounce this word, but it's called, I guess it's scatel, was used commonly in the ancient Greek, like 7th century BC. So you can see that this, you know, art is very, very old. And we humans have been using it for a long time. So this is really cool that they will have a cylinder, and then you write a message in a piece of paper, like alphabet at a time. You go down, and then what you do is, like, if you put the paper onto the rock, it has to be certain diameters, right? So maybe, I don't know, 10 centimeter, could be, you know, 30 centimeters. It depends on the dimension of the rock right here, and then the message will appear. So that is also a very ancient way to try to scramble the message. Now, if you hide the rock, and then you just have that piece of paper, someone intercepted it, they don't know what the heck is this, right? It's not going to be giving you a message right away. So that's what happened. That is how you can decrypt. That's what we call decrypting the message, sending it in code. Then the people has to decrypt that. Vehicle has to know how to decrypt the message, working the message, you know, putting it on the rock in this instant, then, you know, the message appear. So that's a very, very old way to do it. And everybody probably know about Caesars. And then there's also a Caesar cipher that we were talking about, and then use the Roman time. So this is what we call a shift cipher. That means that you're only shifting the alphabet, like on the right or on the left. So if you line up all the alphabet right here, if I intended to send my name, Jennifer, right, J-E-N-N-I-F-E-R, so forth, but I can actually send, maybe shift it to the right 5 times. So 1, 2, 3, 4, 5. I'm going to send J. Instead of J, I'm going to send R. Instead of Y, I'm going to switch 1, 2, 3, 4, 5, and then send an M. So when you have those scrambled message, you really wouldn't know what is going on. So for example, in here, what we call the message that you intended to send, we call a plain text. So that means that, you know, the plain text is the message itself. So I say, okay, meet me at noon. You know, you got some secret going on. I want to talk to you at noon, but I don't want people to know what time we are meeting. So we're going to send you a secret message and say, hey, John, meet me at noon. So then when you look at the ciphertext, will be like that. Now, usually they don't have spaces. The spaces is just to help us to understand there's actually 4 words in here, and it's corresponding to the plain text right here. So we usually write the plain text in lowercase, and we write the ciphertext in uppercase. And then again, there should not have any spaces in between. So that would even more confusing, right? I mean, if you have like, okay, 4-letter words, 2-letter word, 2-letter word, and then 4-letter word, and then people can kind of guess. But if you put it all together, you don't even know, it could be 6-letter word and then 6-letter word, right? 2 6-letter words. So that's why that we try to, that's what we meant when you say, when I say sending, in code and then in ciphertext like that. So again, this is just a Caesar cipher is a really simple shift. And then once you have the alphabet, let's say M, instead of cell M, I'm going to, okay. So this is just like no shift at all. So if you look at M and then it's a P, if you look at E, it's an H. So this is basically, I'm not even sending and wait a minute, let me see what I wrote. Okay, using if it's okay. This is why if I shift my alphabet 3 times. So that means that if I insert A in here, I'm going to the first letter. If I want to send an A letter, I'm shifting 1, 2, 3 times, and I have a D in here. So if I want to send a B, I will send a E instead. So this kind of like table kind of help us to kind of like corresponding the plain text, which is the lowercase one, and the ciphertext on the uppercase one. So if I say meet me at noon, if I use this table, I'm going to say, okay, M is going to be P, E is going to be H. I do have 2 H's in here because it's E, and then W. If I want to send T and I'm sending W. So remember, this is like shifting 3 times. So you can shift it anytime you want, any number of times. You can shift it 10 times, you can shift it 20 times, you can shift it 5 times. So that is crucial, right? If you do not know how many times that you shift your alphabet, you're not going to know how to decipher it. So when I decipher it, when I unencrypt it, that means that I'm just going to use the table. Let's say P, I'm going to look at P, and I'm going to say, oh, that's an M. And then I'm going to look at H, and then that's a E. And then so this table definitely help. And then it depends on how many times that you switch. And if people don't know about it, they're going to have a hard time to know your original message in here. So, and as I say in here, the key is really, really crucial in here, because the shifting 3 times is your key. The 3 is actually your key in here. So if you want to express this mathematically, you're going to say for encryption, I'm going to encrypt. So K is the encryption function, so to speak, encrypting the X. X is my plain text in here. So my plain text plus K, and I have to mark 26 because this is called modulo mathematics. This is a completely like different mathematics that you got to get familiar with, and we do use a lot of modulo mathematics in cryptography. So we will talk a little bit about that. I don't want to get too deep into it, but we will talk a little bit about what is this modulo mathematics is about. But in here is really simply that if I turn my alphabet, if I add 3, right, that's the key, and then I will decrypting the text, which is like in here. However, if I want to, from this text, from the ciphertext, I want to go back to my original message, I'm just going to do minus the key, right? So this is the opposite direct. If I plus 3, and then to decrypt the message, I'm just minus 3, and then I will get back to the original message, say meet me at noon right here. So that's pretty much like the kind of like that you need to get used to the vocabulary of the cryptography. So we do talk a lot about plain text, which is like just in plain sight, right? It kind of pretty self-explanatory. It's just like, the message that you intended to send, and you usually use X to represent the plain text. And then Y is your ciphertext. Ciphertext is like all scramble up the message. The message is scrambled up right there, and you represent it with Y is the ciphertext. And then we often use K as a key. So in here, in this case, the key is 3. Without the key, you're not going to be able to decipher the message. You can guess, but it will take you a little bit more time. And that's the whole point of cryptography, that you're going to, right, not hiding the message, but encrypt the message, sending the message in code and cipher or scramble up, and people do not know what you're intended to send, even if they intercepted it. So that's the whole point of cryptography, actually. And then it might fail to mention about, so when you're sending a message, this is going to help the confidentiality of your message, which means that you want to keep your message secret. You want to keep it confidential. You don't want anybody to know about it. And that's what we call the cryptography. Encrypting the message is actually help to protect the confidentiality of the information. So later on, you can see that there is another way. Sometimes you want to protect the integrity of the message. So that's two different, what we call security objective. So it's different purposes. So we're going to use different methods for it. And a lot of people get it confused. Like they will say, oh, cryptography is just about hashing. Hashing is the way that to protect the integrity of the message, but it's not. Cryptography is actually really try to protect the confidentiality of the message. I don't want people to know what I'm sending. While the integrity is protecting what you're sending. I don't want people to alter my message. If I'm going to send you $2,000, I don't want you to say, hey, you said you send me 20,000 instead, right? So the integrity of the message, that is another way to protect it. And we will talk briefly about that. And then come back to the cryptography, come back to the Caesar cipher. So it's really cool. I mean, everybody can do that. You just put two wheels, put alphabet on it. It can be English alphabet, it can be Greek alphabet, it could be Spanish alphabet, and then you just put it together, and then you just line up right here. In this picture, it is the shift to 3. So you can see that, you know, if your A is lined up to D, B is lined up to E, Q is lined up to T, P, this is O, M, N, O, P, Q. This is the Q line up to T. So you can use this, and then the purpose of the rule is you can rotate. So you can rotate 3 alphabets, or you can rotate 5, you can rotate 10, and then it will give you the corresponding alphabet to send. So now, but this is good, right? People get your message, they don't know, but it's also, it's not that secure because you're just shifting a number of the spaces of the alphabet. But you know, if people are kind of smart enough, they will probably kind of figure out, you know. And again, when you look at the message in here, the keyword is really meet me at noon, right? At noon right here. So if let's say people are really smart and they would say, oh yeah, wait, HH, that is repeated, H repeated again, right? So you would say, because what we were talking about, like when you write a message, what is the most common alphabet of the English letters, right? So later on, we'll look at a little bit about frequency analysis. So even though you think this is safe, but unless people, there is a way for people to figure out, you know, what is this message about? All they have, okay, if they can guess this one, meet me, okay, meet. So you're meeting someone at a certain time. If you just decipher part of the message, that get your enemy or your, you know, whoever, your adversary, a little bit clue about what you're trying to do. So there is a way. So we say that there's really no way that can 100% securely send a message. There is always a way that people will break your message. So we'll talk a little bit about analysis, frequency analysis in a crypto analysis section. So when you have a way to decrypt the message, of course, the natural ways people try to break the code, right? When you write the message in code, and people are tending to try to, let's see whether there's any way that I can break that code, and then try to get the original message. So this cipher is relatively easy. It's just switching, you know, 3 spaces of your alphabet. One of the things that is a little bit harder is this called Veneer cipher. Veneer cipher, now we are going, we're going more modern time now, is 15th century in advance. And then they this is like what we call the Caesar cipher is called monoalphabetic substitution. So you basically substitute one alphabet with another alphabet. So you mono, that means you just substitute one alphabet to another alphabet. So if you look at this wheel, you can say I'm substituting A with D, I'm substituting N with Q, and that's only one alphabet that you're substituting. Now, Veneer cipher is a little bit complicated because they probably realize that, hey, you know, that's too easy. People can probably you know, guess it, or people can figure it out. As I say, you know, figure out the most frequent letter in the alphabet. They probably figure out, you know, what you're trying to send. And keep in mind that you don't have to decipher the whole message. You can decipher part of the message, and then you gave your enemy or your adversary some idea of what you're doing. So that's very crucial when you think about it during World War II. And then you sometimes maybe the parcel message can help them, you know, move your troops, move your ship to somewhere else, perhaps. But of course, the ultimate goal is always for the enemy or for the adversary to understand and decipher your whole message. So for this Veneer message, it is not monoalphabetic substitution. That is actually, you will have a keyword actually, and then you will switch your alphabet, not just with one-to-one correspondent, but you know, it depends on the table. I'll show you the table later on, and then it will switch the alphabet, substitute the alphabet in a different way. So for example, when you go see this message like, okay, meet me at dawn. So you really easy to figure out that, okay, H happens 3 times. So that's probably, you know, this is all corresponding. E is always corresponding to H. And O happen to always correspond in R, you know, Q, R, R, N. I mean, how many words that you can say first and last alphabet is the same, and the middle 2 alphabets are the same. So that could be really easy for people to kind of guess, you know, what the word is. While in here, when you have the Veneer cipher, is a completely different story. Instead of one-to-one substitution, I am going to substitute, for example, in here, I want to tell you attack at dawn. And then this is what we call plain text, and this is going to call ciphertext, right? So when you look at T and T, T is first T is like corresponding to B, and the second T is corresponding to I. So you are coding the T or encrypting the letter T in 2 different ways instead of just one way, like the Caesar ship. So this is a little bit more complicated, a little bit harder for people to try to decipher it. So oh, I have it right here. So this table is kind of help us. So we need to look at this table before we come up to this table. So this is how the Veneer cipher work. So can do the whole screen, but you get the idea. I have A, B, C, D, you know, I have all the alphabet on the top, I have all the alphabet on the bottom, on the column and in the row in here. So what I actually do, I have to have a keyword, right? This keyword can be 5 letters word, this keyword can be 10 letters word. This keyword is usually, you know, relatively simple to get to making sure that the encryption is okay, but the decryption, right? We want to making sure that when we decrypt the message, it's easy, you know, not much time, but when we decrypt the message, it doesn't also cost too much time either. So that you don't want to have people spending 10 hours trying to figure out what you try to send, right? And then that algorithm or the method has to be as simple as possible, but at the same time, it's a little bit time consuming. So then the enemy will not be able to get your message that easily. But the process has to be almost like, you got to be smooth, you got to be not simple is not the right word, but you got to be able to, for people the other side, once they get the key, they will decrypt your message relatively quick to get your message. So in here, I think I set the keyword, what do I set the keyword to be? I can't remember. Oh, I set the keyword to be cipher. So that is my keyword in here. So what does that mean? It's like I'm going to like the A, I'm going to look at the C column right here. So I say attack at dawn, right? So the A, instead of like I'm shifting it so many times, I'm looking at the C column in here. So first column in here, I mean the row in here. So your plain text, you're going to look at the columns in here. So when I have an A in here, I say, oh, the first the keyword is C. That means that this is actually a shift cipher. Each row is a shift cipher, right? It's a mono alphabetic shift cipher. So what Caesar's cipher do is each of the row is actually Caesar's cipher, right? First row, I don't have any shift. The shift is 0. Second row, I have a shift is 1. I'm shifting 1 alphabet over. Third row, I'm shifting 2 alphabet over, and so on. And when you get to the last row, and then I'm shifting all 25 alphabet over, right? And going to the last alphabet first, and then go back to A, B, C, D, E, F, G, right there. So then when I encrypt the message, I'm going to see which row to use. Each alphabet in here on my plain text is going to have a different shift. So that is just making the cipher a little bit harder for other people to guess the message. And as you see in here, the T is going to be encrypted into 2 different alphabets instead of the same alphabet. So again, A, I'm looking at the A section, A columns in here. And then I'm saying, okay, the first word is the first alphabet of my keyword is C. That means that my first alphabet of my phrase has to be shifted 2 times, which is right here, C. So then that's how I got the C right here. So, and then the T, I'm going to look at the I. That means that I'm going to shift it, I don't know, 1, 2, 3, 4, 5, 6, 7, 8 times. So I'm going to look at the I for my second alphabet. My second alphabet is T. So I'm going to look at the T columns, but I am going to look at the I row, and then I'm going to be a B right here. So that's why that we have right here, the second letter is B. The third letter T, I'm not going to use the same shift. I'm going to look at the row P. So I'm going to look at the row P in here, and I'm still deciphering, I'm still encrypting the T right here, and then I'm going to look at the P in here. So I'm going to have the alphabet I in here, and so on. So then let's say and then when you say, okay, attack, that's 6 letters, and then the K, I'm going to look at the R column. And then when you go back to the 7th letter of your plain text, it's going to repeat again, cipher. And then so in this A, I'm going to look at the C again. In this T, I'm going to look at I again. So CB and CB right here. And then dawn, I'm going to look at the P row, and so on. So is that kind of makes sense to you guys? And it's a little bit more complicated, just because the more complicated, the better and secure we will have on this message. So this table is very common. If you look at that, if you Google it on online, they usually tell you this Veneer cipher is using this table in here. Now, again, this cipher, it doesn't necessarily have to be 6 words. It doesn't have to be like, this is 12. It happened to be 12 alphabet, and it has a 6 alphabet. It doesn't have to be even either. So I could have the keyword A, say apple, and which is 5, right? And then you just repeat until your last alphabet in here. It doesn't have to use up, so to speak, all the keyword. You can have keyword, say Ecuador, or or you can have keyword, say mathematics. It can be longer than this text as well. So it really depends. So again, we have the plain text in here in blue. We have the ciphertext in red, and we have the key is the keyword which is Cipher right here. And that is the Veneer, the Cipher in here. So now, Caesars and Veneer Cipher is very similar, right? They're all about shifting certain certain number of alphabet. So while in Caesars, I'm always using 3 spaces or shifting 3 times. While in Veneer, it depends on the keyword. As long as people don't have the keyword, they will have a hard time to figure out how many spaces you shift. But even in here, you can see that, okay, AT, the first one, it just happened to be 6 letters. And then my AT on the second at and attack the AT is actually deciphered the same way, right? So in here, if you want to break, so to speak, break the code, you have to know the length of the keyword, right? That definitely make a difference in here. So we're just having a couple of exercises. Maybe I can send you the notes that you can do it a little bit and then see. Again, when you doing it, so to speak, backward, when you do the decryption, remember if you shift the row and you're adding, let's say this keyword is 11, when you do the decryption, you're going to be, doing it backward, minus 11 instead. So I'll send you these 2 exercises just for fun, and then you guys can look at that. Again, if you have a Ciphertext, we usually don't have spaces right here. So it make it really hard. And then you just look at this word, you have no clue. Now in this exercise, I tell you, use a Veneer Cipher. But if you look at this Ciphertext in here, I'm just like, okay, first of all, what do you need to know? You need to know what method do they need to decrypt the message, right? So it could be Veneer, it could be Caesars, you don't know. And then second of all, if it's a Caesars, we have to know how many places that it shifts. So that's adding another level of complexity in there. If it's a Veneer, we need to know what keyword do you use. And then that will be a little bit more harder because different keywords can resulting in different ciphertext. So that's why that the Veneer Cipher is a little bit, the more complexity that we have, the more secure that you can have in your message, the making sure that your enemy or your adversary is not going to be able to decipher the message or the code. Or at least take them a long time. By the time they decipher it, maybe, hey, the event or the attack is already over, they don't know exactly where or when. So that's like a couple of them that is very old method and relatively kind of simple, shifting, different places of the alphabet. But the other one that is, we're getting into the 20th century right now, that the Hugh Cipher. The Hugh Cipher is another what we call polyalphabetic crypto system, so which is the same as the Veneer Cipher. Veneer Cipher is also called polyalphabetic crypto system, or Cipher. Is mean the same. While the Caesars is only mono alphabetic because one letter substitute with one letter. So Hugh Cipher is a little bit different, a little bit more complicated. It involves matrixing in here. That means that you will have to know linear algebra in order to be able to, do the calculation and understand it. So this is, let me see, based on linear algebra, and then who invented it? Lester Hill, I believe. I'm not sure this is a British or American, but someone named Lester Hill in 1929, based on linear algebra, and then they have invented this crypto system or this cipher. And then it has to be a square matrix. So that means it's very, if any of you have linear algebra before, you will know that it's very computational expensive actually to do matrixing, right? So then that add another level of complexity on your cipher, and then it take a lot of, if you have to have multiply, let's say 10 by 10 matrix with another 10 by 10 matrix, there's a lot of work to do. There's a lot of computational you need to do. So we usually say matrix C multiplication, the bigger it is, the more time that you will take, the more computer resources you will take. However, if you just 2 by 2, 3 by 3, okay, you can still do it by hand. Now remember, back in 1929, there's no computer, there's no calculator. A lot of people just do a lot of those deciphering. Even during World War II, right? That's not really personal computer that like we have right now. A lot of this is we have to do it by hand. So definitely take a lot of time. So if you have this, when we were talking about that, we want to be able to decrypt the message rather quickly and send it. And when Bob, like your recipient, and when they receive the message, the system has to be relatively simple also, and then quick to decipher the message and making sure that they got the message in time. You don't want to invent a crypto system that is so complicated, it take me 5 days to decipher the message. And then by the time I decipher the message, it's already, gone. So it's like almost like twofold when you deal with crypto system in here. And sometimes when you see some of the real crypto system like that we use today, you can see that it has to be like, the algorithm has to be quick to do, but at the same time, it has to be complex enough that, if people intercepting your message, they will not be able to compute, rather quickly. So when we use matrix C, square matrix C, that's why we use like, 2 by 2 or 3 by 3, that's like doable by hand. When you get any bigger than that, that's just like too hard to do. So why do we limit it into 2 and 2? Because of the linear algebra, the way that the multiplication of it, and it has a dimensional restriction on it. So you cannot just say, hey, I'm deciphered July, the whole word, I'm just going to, you can use 4 by 4, but again, it will be much more complicated and mistakes will be made. So I'm just going to split up. I'm going to send you, the plain word July, but I'm going to actually decrypt the 2 at a time, JU first and then LY and then second. So for this, remember when you decrypt the message, you have to have a way to decrypt the message. So, like in the Caesar cipher and the Veneer cipher cases, we add 3 spaces, and then when we decrypt, we subtract the 3 spaces, right? Going backward, 3 spaces. However, in this Hugh cipher, you're not going to be counting spaces anymore. You're going to use the matrices. So then your key will be the matrix. So people know your matrix, they can decrypt the message right there. But in order to decrypt the message, going back to your original messages, you have to be able to do that. So that's why that if anybody take linear algebra, you know that each matrix is not really invertible. So that means that my key, my matrix has to have an invertible matrix that allow me to do the decryption going back to the message. So not every single matrix is qualified, so to speak, to be the key. So you have to be careful when you choose your key. So it happened to be pulling this example from the book, and then I'm going to have the key with this matrix right here. So again, it has to be square. So if you have 2 letters, then I'm going to use 2 by 2. If you have 3 letters, you can do 3 by 3. If you have 4 letters, I can attempt to do a 4 by 4. But again, the computation is getting messy or expensive there when you do matrix multiplication. So we stick with the 2. The reason that we do this is because we're going to equip the JU first, because you have to be, if you have a, let's say in here, 1 by 2 matrix, you have to have a 2 by 2 or 2 by 1 matrix in order to do the multiplication in here. So that dimension has to match, because the matrix computation is like, you have to do 9 to match 11, 20 multiplied by the 3. So if you have 3 1 by 3 matrix right here, you're running out. You do not have another number to multiply, so to speak. So there's a lot of linear algebra calculation there, and you got to understand how it works in order to use this cipher. So, for example, I take this matrix C as the key, and then I'm going to convert the J and U into their numerical counterpart or the numerical correspondent, A being 0, B being 1, C being 2, and so forth. So sometime I will have that table in there so I can turn some of the alphabet into numerical order, and then you'll be able to do it. So I have the equation will be J is happen to be 9, U is happen to be 20. And then so I use this key matrix C, and then I multiply it, I get 3 and 4. And you look back into 3 and 4, it corresponded to the alphabet. 3 is actually D, 4 is actually a E. So now I actually decrypted the J to D and the U to E, right? So I'm only taking care of 2 alphabet right now. So now I'm going to do the LY, the same thing again. If I do the same operation, I use the same key, I will get the L to be L, or L to be L, actually, okay. Y to be W. So now I encrypted my plaintext July to DELW. And if you look at DELW, it doesn't even spell anything. So then you keep your head scratching and it's like, okay, what is it? And and then so be able to go back to do it, you will have to, I don't have the example here, but you will have to using the correspondence, say 3, 4, I have to multiply this invertible matrix E to get back to 9 and 20. So that, as you can see, using this Hill cipher, there's a different level of complexity in there. And if you have the ciphertext DELW, it's like, well, first of all, you only have 4 letters, it gets really hard to guess. And then you don't know what, first of all, you don't know what method they use. It could be a mono alphabetic cipher, and it could be other method instead of the matrix E. So using matrix E, using Hill cipher. So even if you know the Hill cipher, oh, this guy is really clever, they're using Hill cipher to do this decryption. So you still need to know your key, right here, in order to do the decryption and the decryption. Once you have choose the key, when you choose a matrix, there is a way to calculate the invertible matrix E, matrix that you will use for decryption. So basically, the math behind it is like if you multiply, if you do a matrix multiplication with these 2 matrices, it will give you 1. It will give you what we call identity matrix. So it'll give you 1. So same thing with the Caesar's cipher, right? If you add 3, you minus 3, you'll get back to the original message. Okay, let me stop right here and see anybody have any questions that I can answer before I go into a very interesting World War II apparatus called Enigma machines.
Okay, we have a couple of questions.
Okay.
Actually, one is made by me, but let's read the other person's question. Romeo Costa, at Hill cipher, you are using a mod 26 again, right?
Say again.
In Hill cipher, are you using the operation modulus 26 again?
Oh, yes. Good question. That's right. Because like if you have a multiplication of more than 26, definitely it's not going to give you the corresponding, alphabet. So yes, you're right. I do fail to mention that. Thank you for clarifying that.
Okay. The another question is, but I think you responded already. In the Hill cipher, the bigger the key matrix, the more difficult to crack down the key, but it's more difficult also to to make the inverse matrix and everything. I mean, it's gonna be
Yep. So let's say if I want to decrypt like my name again, Jennifer, right? There's 8 alphabets. You can get an 8, 8x8 matrix, but usually we don't do that because it takes a lot computational time or computational, and again, during that time, people use it by hand, but now we do have, computer to help us, but even that is going to be really expensive. You rather than splitting up into smaller chunks, and it will be faster, it will be easier. So that's why that even with July, you split up into 2 and 2, and then you use 2 by 2. If you want to be 3 and 3, you use 3 by 3. You want to have 4 and 4 alphabet, you do 4 by 4. But the higher dimension you go into, the more difficult to go to do the computation. So again, the key for cryptography is really tricky. You need to find the algorithm is really like it's easy to not only encryption should be really easy, but the decryption should not take like a lot of time or complicated as well. So later on, you can see, that's not always like, you just do the opposite for the decryption, but you need to making sure that your communication party, you got to be able to decrypt it relatively quickly once it has the key and it has the the keyword, it has and then know what to do. So that's really the key in here. So it's not that easy when you try to invent a crypto system in here. So any of you can go ahead and invent, right, a crypto system, but you got to design it in a way that it's really hard for people to crack without the key. And at the same time, if you do have the key, the calculation has to be rather smooth and then quickly to decrypt your message in here.
Okay, we have a couple more comments. Mario Ruiz says the inverse is also a modular inverse, not the usual inverse. Antonio Chong says, in the example for Hill cipher, should J not be C and U not be D?
Okay, let me see. The first question is a multiplicative inverse. So that means that these two matrices multiplied together, it has to give you the 1, 1, 1, 1 identity matrix. And that's how that you can do the decryption, because your matrix has to have an inverse in order to do the decryption. I'm not sure I answered that question. And for the second question, I bet like J and U, using this method, J is encrypted to D, U is encrypted to E. We will do the same operation again, but using a different like L and Y. And then in here, 9 and 20, probably other numbers, and then using the same key, and then you will get the different answer, and the different answer should be corresponding to L and W.
Oh, because A starts with 0, right?
Yes, A is always started with 0.
Oh,
so
yeah,
let me see. Yeah,
definitely.
A is always started to 0. So when you do modulo mathematics, it's 0 to.
Yes.
Oh,
no,
maybe
you
I
have
have
below,
it later
below.
on.
You already passed. You already passed
right here.
at the end of that page. There we go.
Yep. So A is always to 0, and then Z and Z is always to 25. So when you do modulo 26, right, mathematics is always 0 to 25. 26 will be 0.
All right. David Andres says, for a linear algebra project, I use modulus 67, counting caps and special characters and spaces because C_67 is a field. Okay, talking about algebra, I think. Yes,
we will talk about the field tomorrow, not tomorrow, Wednesday. So yeah, it is a lot of, you do go into field and rings and groups a lot. So those kind of mathematics is also behind the cryptography.
Okay, good. So let's continue. Thanks. Thank you, Jenny.
Okay, great. Fantastic. So Enigma Machine. So if you have not seen an Enigma Machine, it is used during the Nazi Germany to encrypt their message, and then this is what it looks like. So I was like pretty lucky. I know what it looks like in the picture, you know, but you see in person is a little bit different. So I went to Washington, D.C. They have a spy museum there. And then that was right here in the Enigma machine. And it was really ingenious, you know, ingenious invention there, you know, thing about doing that time. Give very, very, you know, complexity. You basically, I believe, if I remember correctly, I think it's like we actually went out, I think Americans or the British or the French, I don't remember which country, but we actually has to have that machine. We possess the machine to decrypt the message in there. So it is extremely complicated. It has 3 rollers in here, which set the key. That is the key in here. And I think some machine, they actually have 4 roller in here. So there are 3 roller as the key. Not only they have the key, they also have this, like, potentially have 13 pair of wires to switch the alphabet before they even encrypted the message. So that adds another level of complexity on top of it. Let me see what I wrote in here. I think that's pretty much what I said in here. Sometimes they have a 4 roller, there's 13 pair of letters, but they don't always use 13 pair. I think the most they use is like 10. So for example, if I want to say, meet me at dawn or attack at dawn, I will, instead of like ATTACK, you know, actually equipping those alphabet, I'm actually going to switch the alphabet with another pair, another letter, and then I'm going to send decrypt it the way that it's supposed to be. So it definitely adds another level of diversity in there. And it just like really, really cool. And then they have a keyboard in here. So what they do is like, when you push, let's say A or C or whatever K, the keyboard in here, some like your cipher text will appear, light up in here. So it's basically the machine doing automatically for you. A, okay, ciphering to maybe the letter is G, you know, and then I push K, and then the corresponding ciphertext will be, you know, D or something like that. So it is a machine that can do automatically in there, and equip and decrypt on it. And when you decrypt, you know, you basically have the same setting and then push the same button, and then your plain text will be appear in here again. So even with 3 rollers, that is the key. You don't know what the, you know, the keyword is, right? So if you only have 3 rollers, you already have 17,576 combinations in here. So even with just that 3 roller, you have to guess 17,576 times to get the right one, right? By the key. And there's also 6 possible positions, and each of the position that you play, if the A is on the first roller or A at the last roller, is definitely going to decrypt the text differently. So, and then you have all this like 6, you know, like potentially 13 different pair of wiring in here that allow you to switch the alphabet before, excuse me, before they actually send, decrypt the message. So that's again, you know, they can use 13, they can use 10, they can use only 5 pairs, you don't know. So that's why that is really, again, it's pretty fascinating, you know, machines in here. So the complexity, so I mentioned it many times, the complexity is the key concept to crypto system like the Enigma machine. The more complex it is, the harder for the enemy to try to decipher your code, right? But nonetheless, this is, I think, is a Polish mathematician. He actually break the code without knowing everything. So everything that, you know, that this machine does is have the mathematic, you know, background with it, right? You have probably show certain patterns, even though despite that they use the roller and the cable that should be pretty awesome. I mean, usually the credit go to this person, Marin Majeski, but you know, that's in reality, it's probably like a group of mathematicians that is actually breaking the code. So again, you know, there's tremendous mathematics behind all the crypto system that definitely a advantage to study mathematics and all kind of mathematics. Like you know, the last question I had before, you know, yeah, there's a lot of fields and groups and rings, you know, theories behind the crypto system as well. So you have a chance, you know, you can Google it, you can see how it works. It's pretty cool how they do it. And now that you have seen certain, you know, crypto system, and as you see, when the time, you know, when there's more modern time, the crypto system is getting more and more complex, and the complex is good because then your enemy is not going to be able to decipher your message, but at the same time, the algorithm need to be easy enough to decrypt, right? So in this case, when you communicate, the other party, you just have the same machine at the same setup, right? You tell them, hey, I got this 3 roller is ABC, and then I got this like 5 cable is switched, you know, switching this like pair of alphabet. Then as long as you guys have the same setup, same machine, you can easily to decrypt your coded message. So that is what really, again, the heart of cryptography. But without having the machine, without knowing the position of the roller, the alphabet or the key, without knowing all this cable, you're not going, it will take you a very long time to guess. You're probably intercepting a lot of messages in order to, you know, making sure that, you know, and the thing is, like, I believe that they actually switch the rotor every day. So every day you have a new keyword, new key, so to speak, in here. So that even make the message really hard to decipher, because like, and then the cables out here as well, I mean, they change it every day. So that definitely at another level of complexity in here that you will not be able to do it. And then as far as how this person did it, you know, again, no matter what you are doing, there's always mathematics, there's always pattern behind it. And in fact, I have to go back and see how this guy actually did it. But that is also the key is the key, so to speak, right? The key is really the key. I think there was a story behind it. A Polish soldier, they actually get a hold with the key that they use. Like, you know, they would just write, I don't know whether they write down the key or not, but they were just saying that this is the key that they use this day and tomorrow and the day, right? Now that key has to be communicated with the other party, like whoever your communication party on the other end, they have to know the same key, right? So that got to be some kind of like, that is the problem actually, and later on you will see that you have to share that key, and then that key has to somehow, you know, make it to the other party, and then they either by, you know, someone delivering it, and that and give you the chance to intercept the key. And I believe that one of the Polish soldier or something, they actually, you know, intercepting those key, and then they'd be able to decrypt some of the messages in there. Or the other story I heard is like they were decrypting, I think, like the weather situation, and then it's not hard for them to, as I say sometimes, right? You can decrypt the partial messages, and you would be able to, you know, kind of guess what they are doing. I think I can't remember. I read the book a long time ago, so don't quote me on this. But I think there was one of the story also that is like they were like talking about the weather situation, and then that's how they were be able to, you know, decrypt or break the code, so to speak. And behind it, there's actually a lot of women behind it, and they deliberately, the British and American, they deliberately hire someone, you know, people that is really good at puzzle, good at figuring things out, you know, and of course, mathematician as well, and then be able to break the code. So it's a pretty fascinating story behind it. So if you have a chance, you know, go and dig out those story and then read about it online, maybe. So that's some good definition in here. As I say, plain text is usually lowercase. This is the secret message you intended to send. Ciphertext, we use it a lot. This is like basically the jargon of the cryptography, those special words that we use, you know, common words that we use in the cryptography field. So ciphertext, again, is uppercase. Those are the code or encrypted message that derive from your secret message. And the key is the key. The key is really important, as you can see. So to use to encrypt and decrypt the messages. So for the example of the side tail, it is the diameter of the rock. So it could be bigger, it could be smaller. It might give you a different messages. Without knowing the diameter of the rocks, you will not know, you know, what message it will appear when you roll the paper, you know, onto the rock. So again, that information has to be communicated, right? Hey, by the way, hey, Caesars or whoever, you know, John Smith, you know, we are going to use the 10 centimeter rock, you know, so that message has to be sent. And if that message itself being intercepted, you know, then people will have a chance to break the code, so to speak. So for the Caesar cipher, it's the number of shift, that's your key in here. For the Veneer cipher, that is the keyword that you are talking about. And then for the Hill cipher, is your matrix C, is your key, but not any matrix C, right? It has to be invertible matrices in order to decrypt the message. So for the Enigma machine, is really the rotor. The rotors are the key. As far as the cable count, the table, sometimes we call it like, what was the word? It's pre-processing your messages before you decrypt it. So that means that, again, right, even you decrypt it even you know the rotor, you decrypt it, you will know that a certain alphabet is always switched. But that is kind of easy to figure out as well. If you kind of like looking at the message itself, it could be figured out. But the key is really, you know, on the rotor itself, the 3 or 4 rotor and the position of the rotor. That is the key for that crypto system in here. So by now you should probably understand what a crypto system is like, right? A crypto system is basically a mechanism, a machine, algorithm, or whatever, you know, things that you need to use to scramble your secret message and output coded message. And if intercepted, it will make no sense. People will not just read your message and immediately know what it is. They have to, you know, take time to analyze it, so to speak. So the more complex a crypto system is, the harder for the adversary to figure out what the original secret message are. So we all agree with that. That adding the complexity, you will adding some sort of adding security, but at the same time, you need to make sure the algorithm to decrypt it is easy enough for your other partner to do, so it doesn't take a lot of time to do that. That's why the key. Without the key, right, like you will really have a hard time to try to decrypt the message. So, however, no matter how complex you design your crypto system is going to, there's no absolute security. So every single crypto system, sadly to say, it will only a matter of time someone will break the code. So with keeping that in mind, so you got to kind of figure out, okay, I know that it's not 100% secure. So that's why sometimes it come up, it's like, okay, time is very important. If this system is going to take you 4 years to break it, okay, then, you know, I can send a message and then by the time you break it, it's no use already. And a lot of time that, let's say during the World War II, is also, I mean, I want you to attack at dawn today or tomorrow. And then by the time that, if you do not know the message immediately, it take you a few days, even a few days to decipher the code. it's not going to use, right? So just keep that in mind, that just because you have a very complex crypto system, it doesn't mean that it's 100% secure. There's nothing 100% secure. It's always a matter of time. So that means that we just want to make sure that our adversary will take a lot of time and try to decipher the message, right? And break the code, so to speak. So it's not like something that it could be simple enough that they can break it in an hour or days. At least take years. That would be ideal. But eventually they will. So if you want to send a message like 4 years from now, meet me at the bridge, don't do that, right? Because like people might know that. But as long as your message is like time sensitive, like I need it right now, and it take them a lot of time to figure out the message, that's fine, because then by the time they figure out, that's really not secret anymore. So in mathematically speaking, we define it mathematically. We define it as a phi tuple. P is usually a finite set of possible plain text. So it's a finite set of the plain text. C is the finite set of a ciphertext. Key is your key space. You could be a lot of different keys. It doesn't have to be used one key. It could be different key, different time. It could be multiple keys. And then E and D is just your encryption and decryption algorithm. So that's what I was saying, that your encryption and decryption algorithm has to be easy enough to do and quick enough to get the answer for other party to decrypt the message. However, but the system itself has to be complex enough that if adversary or your enemies interrupting your message, it will be hard for them to know what to break the code. So for each key in the key space, there's an encryption algorithm using that particular key. It will also have a corresponding decryption rule using the same key, and is in the decryption algorithm in here. So each encryption algorithm with the key is going to turn the plaintext to the ciphertext. The decryption algorithm with a particular key will be turning the ciphertext to the plaintext. They are and it has to be functioned this way. You decrypt the encrypted function or decrypt the encrypted message, you'll get back the message itself. So it's not just any algorithm will do, but this algorithm has to fulfill this in order to get the message itself, right? And it has to be for every plaintext element in X and P. So every single plaintext go through this decryption of the encryption algorithm. It has to get back to the plaintext. Otherwise, it's not going to work. Otherwise, you're not getting the right message that you send. So that's kind of like mathematically when it can define like this way. So we're talking about modular mathematics. So I want to introduce a little bit modular mathematics in here, which is like you already know. Most of us already know. Looking at the clock, we already know modular mathematics. It's not really hard to do it. Basically reducing all the number into whatever classes that you have. Like let's say if you modulo 26, then you just have 26 set of number actually. And then so if you're looking at the clock, so this is might be not necessary, you guys already know, but just go through it. I'm going to mark 12. So that's how you count time, right? So when you have at the midnight, and then your clock will say 0000, right? So that's why this is modulo 24 is 0. 1 a.m. that is just 1. And then all the way until noon, then you had 12 noon, right? But if modulo 12 is marked 12, so your 12 is actually 0. So if you notice that 24 is also equivalent to 0. So any multiples of 12 is going to be equivalent to 0. So when you have 13, when you have like, sometimes we do 1300, 1400, sometimes you say that, or your train schedule, your bus schedule, to use this 24 hours, scheme to make sure that it's in the morning or in the afternoon. They don't want to say PM or AM, right? So when you say 1300, it's 1 PM, right? if you mark 12 is just equivalent. So 13 is actually equivalent to 1. So remember, this is a equivalent, it's not equal, so it's just equivalent to 1 if you mark 12. Of course, when you mark some other number, it's not going to be equivalent to the same number anymore. So, and so on. 23, when you have a 11 p.m., you're still staying up late doing your homework, you know, that is 23 hours, is actually 11 p.m., right? So that's the modulo mathematics in here. And then I'm going to ask you 34, what is that equivalent to what? You know, if I mark 26. So it's pretty easy to calculate actually, you know, anything greater, as you see, anything greater than that, it will be reducing to, you know, anything greater than 12 in here, you're reducing in either 1 to 11. And again, it always starts with 0, modulo 0. In mark 12, the set in the mark 12 is 0 to 11. So it's mark 26 is 0 to 25. So if you have 34, I'm asking you, okay, let's say do your Hill cipher, or when you do certain cipher and using the number itself, the alphabet, to do your calculation, and then you get a number is greater than 26. What do you do? And then you actually, really simple, you just take the, you know, take the 26 off, and then it's 10. So then, okay, so I think I might be a little bit, maybe this is equivalent to 10 instead of 8. I must change the number in here. So that should probably is equivalent to 10. No, wait, you know what? I do it wrong. So let me go back. I looking at my typo in here, that is supposed to be 34 minus 36. So that should be equivalent to 8. So it's just like biggest, actually pretty much is a remainder. So when you have that number divided by the 26, what is the remainder? That is your equivalent number in here. So 34 is equivalent to 8 if you have modulo 26. Now, sometimes you also have a negative. So sometimes when you have -5, you know, what are you going to be equivalent to? So -5 is no different than you basically, so positive, you just keep counting, the number get bigger and bigger. Negative is just basically going backward. So when you have -5, what is it equivalent to? Because we like positive number, and you basically just minus the 5, you come up into 21. So -5 is actually equivalent to 21 modulo 26 in here. So you can go both ways. You can go positive and you can also go negative in here. Formal definition in here, let m be a positive integer. Again, we like to deal with positive integer in here. If x and y are integers, we say that x is congruent to y modulo m. If m is divided, can be divided by x, and the differences between x and y. So again, that is that is what I was saying. That if you say 34 divided by 26, you have 1. The product is 1, but you will have a remainder of 8. Sometimes people will refer this is basically is your remainder in here. So in other words, x is congruent to y modulo m if and only if there's an integer t such that x is equal to mt plus y. So again, see, when you look at this equation in here, you know, and you can say the modulo m, 12 or 13 or whatever is the multiple of that integer, wherever is left over, right? Whatever is your remainder in here, then your x is congruent to that y, and then there's with the modulo of m in there. So this has happened to be very important. You know, this is a very, very simple introduction for modular mathematics. You can probably take the whole semester to just study modular mathematics, or study what we call you know, number theory or abstract algebra in there. But one of the theorems come with this modular mathematics is important for us to understand is the Euler Theorem. So some of you probably heard about it before. Euler is a very famous mathematician. I don't remember how old he is. It's back in the 13th, 14th century, maybe is during those time. And then this theorem really helped us. Later on, you will see that theorem again in one of the Cryptosystem Is the key. to actually decrypt the message, decrypt and decrypt the message. So we are going to introduce a little bit about the Euler Theorem right now. So we'll say, let n be the positive integer. This is the Euler phi function. This is defined to be the number of positive integers not exceeding the n, but they are relatively prime to n. So this is an example in here. So all the number in here, how many number, not exceeding that number is actually relatively prime to itself, right? So one, of course, one is relatively to one. Two, I only have one relatively to one. Two, itself is also always not a prime to itself, right? Two and two is divided by itself. So, and then three, I have one and two is relatively prime to three. Again, three itself is not relatively prime to itself. They both divided by three. Four, I have one as a relatively prime. Two is not relatively prime. Two and four both divided by two. Three is relatively prime. Three and four does not have any common factors except one. Four is of course divided by four. So I only have one and three. So therefore this Euler function give me two. The number of, within one to four, that's relative prime to that. It's not two is relative prime to that. It's the number of the number, what is it? It's the number of positive integer that is relatively prime to itself. Five, you have pretty much, like if you notice that all the prime number is actually pretty much, they have all the number is relatively prime to it, except, their own number, right? Five and five is divisible by five, so you can't do that. So when you go to another prime number 7, I have 6. Another prime number 11, I have 10. That's because itself is not relative prime, so there's only one number left, less than itself. And this is just indicated if you have 12, and I only have 4 number that is relatively prime to 12. So what is 3 and 4 is divisible, 2 is divisible, so it's limited to 1, 5, 7, and 9. That's probably the 4 number that is relatively prime to 12. So maybe the next day, Wednesday, we will talk about RSA crypto system. They actually use computation in this. Is this set of numbers in here? The Zn is the set of integer, and it's just we restricted the number of the integer in this set. And when n is a product of 2 distinct odd prime, p and q, well, all primes are odd anyway. The equation and decryption are done based on Euler Theorem. And then so as I say, when you look at this formula, the number of prime is really, if you look at the prime number, is always one less than itself, right? So if this number, the number of the prime, the number of relatively prime, to the n, you can be calculated by splitting up into the prime, prime factorization, and then -1. That will actually help you. So when you have a bigger number like I don't know, 24, 105, then you'll be able to calculate it this way. And then now we are introducing A and B. If you multiply this A and B, it will be congruent to 1. Your mark is not any number, but it's this particular number in here. It's the Euler phi function in here. So that means that whatever number that it gave you, so let's say, mark, it could be mark 4 if you're dealing with 12. So this is just basically just telling you this is the same thing right here, right? So if A and B congruence to 1, that means that A and B, when you multiply together, t, there is a integer t greater than 1. That can be the this is basically a multiple of phi function, and then +1. That 1 is usually the remainder, right? Remember, for some alphabet. So this is no different than this. This is no different than just expanding the definition of this congruence. Now, so suppose that X is actually in Zn. This little star in here means that this, I think this is a ring actually. This is a field. I won't say it's a field, but I will say that it's a ring. So Zn star, that means that every element in there is relatively prime to n. So it's a little bit different than just Cn. Cn is just like, any number, like C5. That means that you have 5 elements in this set. C10, there's a 10 element in the set. But if you get a star in here, that means that all the elements in there is relatively prime to itself. Not itself, relatively prime to n. So C10, you should have 4 number in there because they have to be relatively prime to that. So we have this restriction. Suppose X is a element in this set. Then we will have, if you have X raise it to the B, and then raise it again, the exponent to A, and then you can A and B, you have the equivalent here. You can put that in the exponent in here. And you can do, again, this is a modulo n instead of modulo phi function, because we turned that into a equation in here that we're not having modulo anymore for phi function n, but in here is a modulo n in here. So if you look at that, doing some tricks in here, you use +1, you can like changing some of the position in here, and then you can let me see, phi n, because AB is congruent to 1 AB, and then that is t to the phi function n +1, and then I can do the 1 is right here, X is 1, phi n t, that is, if it's modulo n, that's actually becoming 1. That's actually becoming t, and then that will become, if you raise the alpha, if you raise the exponent to b and a, and that will be equal to itself, the x. So a little preview that, remember, we always think of X is the plain text. So that is how that you got to back to the plain text right here. When you X, you do this trick, and then you get back to the X modulo n in here.
Actually, we have a question, Jennifer.
Okay.
I think it's related with the Euler's theorem. Is actually who is A and B, and I guess from the last thing that you explained, that is the key for encrypted and decrypting.
Yes, so later on we will talk about RSA system. A and B is just like two random random numbers actually, and that the person that actually choose to be their private key. So A and B is just like a random number, but this random number have that relationship with the Euler Theorem. And if you apply the Euler Theorem in here, as I say, this is just a little preview on that, then you can actually gain back your ciphertext your plain text, and then you can gain back in here. So remember, your plain text go through a encryption system, become a encrypted text, encrypted or ciphertext, and then you have to bring it back to the original message. You have to go through the decryption algorithm in there. So you decrypt the decryption, you decrypt the encryption, you'll get back to the message. So this is basically what it means in here. So A and B is actually, that's really nothing to do with Euler Theorem, but A and B, not nothing to do, but A and B is just like two numbers that you pick, just any number you can pick.
There is another question related with the previous topic that you talked. It was like, you say there is no 100% integrity. You don't have a 100% secure system. I remember in my computer scientist classes in my undergrad, and I remember something that I was called, if I don't remember bad, is a Chinese lottery that was related with if you send the message for all the TVs, okay, a bunch of number of TVs, and those TVs have a little device that can, try to decrypt the message, and if you have in your device, and then you have a lottery that you win, and then you call, and they can, trace back the serious, the what you try, that can possibly break down a code in a short period of time.
Yep.
So I don't know if you want to comment something. Because parallelism it works against
Yep.
the integrity. The possibility to break down a code.
Yep. So that's why that we're going to be going to the crypto analysis system, crypto analysis section. That's the next section that we're going to talk about, and that's what we're talking about. That yes, every single system it can be breakable, and it depends on how you break it. And sometimes you can break it down pretty fast. Sometimes it takes time for, in order to, of course, all the computer scientists and the mathematician, they try to break down the system relatively quick, right? And there's all kind of tricks, all kind of like algorithm, all kind of mathematics, or some computer, like you were saying, the parallel one. Nowadays is really different because you have the computer, that's why that this is usually is under computer science as well, because they have a lot of tricks that, a program or whatever can break the system relatively quick. So that's why that when we do sometimes what we call a system, when you invent a crypto system, there's like 3 types of security in here. So when you need to take so much, we want to have a system that it takes so much computational power that is, we call it computational secure, the system. That means that, you might need to take more computational power than you need to really break the system in a relatively short time. But that doesn't mean that we all know that computational power is increasing every day, every year. So when the computational power increase, and like you were saying, there's some tricks that you parallel computing that it can help you to break the system, then the system is no longer secure. A lot of the time that you don't even need to wait someone to break the system. Sometimes they just say, oh, we can prove that this is not secure right there. So that means that we're not going to be able to use it. So that's why that is really, really especially with quantum computing coming up, and a lot of people will be afraid of that. Okay, with quantum computing, like you were saying, that you can do things parallel and do exhaustive search, in a shorter period of time. And they can find the key. Once they find the key, we're doomed. We can't use the system anymore. So that's why that we have actually what we call post-quantum cryptography, that to avoid this possible break of the code in here. So that's why that you need to keep in mind, no system is secure, and it is needed to have new crypto system, to invent a new crypto system to combat certain adversary and certain methods that it can break the code. So now it will be a great time to go into crypto analysis if there's no more questions.
No more question.
Yeah, so it's really so that's whole crypto analysis coming in place, and then especially during the World War II when you intercept, right? The Germany doesn't care. They send a encrypted message, they send a coded message, everybody can get it, but you don't know what they say, you don't know where their troop is, you don't know where their force is going to attack. So they just send it through the air, and all these people imagine, the Allies forces, that they get all this message, they will desperately want to, decode that. So that's what crypto analysis is about, or sometimes we'll call cryptology, LO, instead of cryptography is cryptology sometimes. So we mentioned again, no crypto system is absolutely secure. It depends on how you're going to break it, and then there might be different way. And I think of the one way, and maybe someone think of the other way, and break it faster. So it's all about how you're going to break the system. So and I also mentioned about the computational secure. So a lot of this, when we introduce some of the crypto system the next time, we'll know that. So, we really have that computational security in mind because, as I mentioned many times before, by the time that people decrypted your message, it might be too late. it might take long time. So that is what we call the computational security. Even with the computing power that you have or the resources you're given, it will take a long time to break the system. So a lot of our crypto system is actually a computational secure system. It is really interesting though with this principle in here. I can't remember how to pronounce this word as Karpov principle of cryptography. They say that a crypto system should be secure. Even everything about the crypto system is public knowledge. Everybody know everything about the crypto system. You know how it works. Let's say in the Enigma Machine cases, you know the rows free. They use a machine for one thing. They use the Enigma Machine. You know they have 3 rollers. You know they have those cables that can be able to switch the alphabet before they encrypt the message. So you need to know all this. Even you know all this except the key. So your crypto system should be secure. Even everybody know how it works, but except the key. So that's I mentioned a lot of time. Because of this principle, we really safeguard the key. And exchanging the key is becoming a problem. And later on, you can see there's different crypto systems that are dealing with without exchanging the keys. So therefore, the key of the crypto system is sometimes referred to as the keystone of the arch. Right? You know, if you think about the arch, the centerpiece is a keystone. Once you take out the keystone, it will fall apart. So that is one of the, kind of like what do you call it? I heard about someone referring to the key, which is kind of makes sense. Keystone. So because of this principle, and we know that the key is the key, so to speak. So, however, there is one crypto system that actually can offer you unconditional security. So unconditional security is like basically, I'm contradicting myself in here. It's like you cannot possibly break it. However, in order to use this one-time pad, it's very, it's not that feasible. Actually, it's not that easy. Not easy. Like it takes a lot of time. It takes a lot of, as I say, remember, you got to making sure that your algorithm, your decryption algorithm has to be smooth enough or easy enough that your communication partner can decrypt the message relatively fast, right? So for this one-time pad, and I think it has used before, I don't think anybody uses this anymore, even though it can guarantee you security, right? I would say 99.9999% secure. I wouldn't still say 100% secure. So one-time pad is an encryption technique that can provide perfect secrecy, and the coded message cannot be cracked. However, as its name suggested that each key is only used once. You can only use the key once, and the key size has to be as big as the plain size text. So you can see, so this is what is actually, so remember the Veneer cipher that I have I have the example, attack at dawn. My keyword is only 6 letters instead of 12 letters. If you would use this one-time pad, your key size has to be as big as the plain size. So imagine you're sending a paragraph of message. Let's just say that I want to encrypt, say, this whole message, this whole paragraph as a message. I have to find a key size that huge, that big, the same size as the plain text to do that. So, and a lot of time that when you send encrypted message, you're not sending like 5 bits or 6 bits, or 12 bits even, or 13 bits, or 26 bits. You're sending a humongous amount of, size. So that is just not feasible. That will really make it hard to encrypt and decrypt the message. So, however, it will guarantee you, because you only use the key once and you discard the key, and then you'll never use the key again. And then imagine the key size and the key space too. You got to have an infinite number of keys that you can use as well, right? So that's why that this crypto system is not really sustainable, and it's not really, good as for the decryption purposes, it's not easy to decrypt. It's not easy to encrypt and encrypt either. It takes so much time, and the key size has to be the same size as a plain text. So that definitely is not practical. It may be for small messages, but however, it does guarantee you, what we call unconditional security. So given that, that's really nobody use one-time pad. We always say that, yeah, you can use one-time pad, but given that it's just so unfeasible, the calculation or the algorithm behind it, the size, especially the size on it, it's just like not really feasible to use that. So when we talk about one of the good example or the best example for crypto analysis, there's a lot of the complicated one. I didn't want to go into it because we have limited time, but one of the more straightforward one is really frequency analysis. So when you think back about the Caesar cipher and the Veneer cipher, and then when you talk about that, you're just substituting the letter with another letter, especially the mono-alphabetic substitution. It's just one letter to another letter. The frequency is still there. People can guess what kind of word that you can use. So that is like some thing that pull out from the internet is really interesting. Actually, the book talk about it too with the English letter frequency. E is actually the most frequent letter, and then followed by T, A, O, and I. And so when you have had a ciphertext, you can also do a frequency analysis, and you can pretty much match up, the frequency and the word that you use, and then you can possibly guess what message that it could be. So for the Spanish, I think a lot of the Roman language is the same. Yi, it seems to be always like the highest frequency one, and in English language, of course, Z is the lower language one. So if you look at all this is all very low, 0.2, even J, 0.2, 0.1, 0.1 percentage of the frequency that's happening in here. And even with your alphabetic substitution, the frequency is still there. Remember, it just happened to be my example using Cipher as the key. My attack, the AT, and the at is actually corresponded to the same ciphertext. So even with Veneer cipher, it's a little more complicated, but then first of all, you need to figure out what is the most likely the number of the key, the length of the key. So is it 5 alphabet? Is it 6 alphabet? Is it 4 alphabet? Again, you can do a 20 alphabet, but then it will just become, it just become, yeah, it might not be that hard, but again, the decryption process has to be easy enough that you can decrypt the message fast enough as well. So I'm not sure this is really the Spanish alphabet, but I just put it up in this website so you can see that, E and A and O and S and N, it seems to have the highest frequency. So if you do want to decrypt your message, that frequency is still there. They can still do the frequency analysis to kind of guess the word. Now, again, for English letter, if you have a T, most likely the next letter, you can tell. Is so you don't even have to decrypt every single letters in every single letter in your ciphertext, that you can actually kind of guess the message is with the frequency, right? And kind of like fill in the blank. So that's what I say, even with the Veneer cipher, the frequency is still there. You can still crack the code. That I'm sure there's other certain methods that out there that you will be able to, crack the code. So now those are like really kind of old school, during the time period that you don't have computer. Right now, it's probably really easy to write a computer program to crack those code already, easily for those. So that's why that we have those new crypto system coming up. You can see the history of the crypto system, it becoming more and more complex. So just to summarize, this is a very simple example. As I say, there's other analysis. There's for the Veneer cipher, and there's a coincident index that you can use, and which is basically pretty much based on the frequency analysis, the alphabet there, that you can actually guess first the number of the number of the letters in the key, 5 or 6 or 4, and then you can actually do that, because you can split it up your ciphertext, especially if you're a longer ciphertext, you split it up, and then you can see how they actually because there's certain right, every six letters you're repeating, so you can actually really can figure out this the patterns in there. So we say in the ciphertext in this cryptography kind of jargon, special vocabulary, we have these 4 attacks that we specify. So first of all, you have the ciphertext only attack. So this is like the old day, the Veneer cipher and the Sesion cipher. All you need to do is, like, if I intercepting the message, I should be able to, I should be able to kind of like figure out, what system they use or what is the message about. All I need is just like a string of ciphertext in here. That might be really good, that is the example will be the Veneer cipher and the Sesion cipher. You don't need to know anything about the key, but you just need to have a ciphertext. That's why I'm saying it's kind of really scary sometimes when you think about that, people intercepting your message and they still can figure out your message about. So, and the other one that is a little bit that you need to do a little bit harder work, you will have what we call is known plain text attack. So that means that you have a plain text, you have maybe a segment of the plain text, a few plain text, and corresponding ciphertext. So that maybe A always map to Y, and then C always map to D, something like that. And then once you have that corresponding, you can also figure out what the message is about. The other one that in here we have chosen plain text attack and chosen ciphertext attack, and both of them is very similar. And you chosen plain text is just basically you have a temporary access to the encryption machine. So you can choose a plain text string, go through the encryption machine, and you can know the corresponding ciphertext. So this is basically the difference between this chosen plain text and known plain text is like, that plain text A and mapping to D, or C is mapping to Q, or something like that. But in here, you actually have the encryption mechanism or machinery that do the mapping for you. So in here, you just know, in here, you for sure that this is actually mapping to a certain plain text and mapping to ciphertext. So on the chosen ciphertext attack, this is just basically it's just the opposite. You have the decryption mechanism. So now, a lot like for the example for the Enigma machine, the encryption is the same. The machinery is the same as decryption machinery. So later on, you can see some of the crypto system is not really that way. But in here, the decryption mechanism in here. So you can choose a ciphertext, and then you can go through the mechanism or go through the algorithm. It can give you the corresponding plain text in here, and then from there you can say, okay, how am I going to give you the certainly give you more information, and then you can potentially break the system. So sometimes when we say the crypto system, it is prone to ciphertext only attack, or is prone to chosen ciphertext attack. So this is like the vocabulary that we kind of use to describe some of the attack on the crypto system. So again, no crypto system is 100% secure except that one-time pad. But even with that, it's a really, really hard to use. Key size has to be the same as the plain text size. So it's not that convenient or feasible to use that crypto system. So with 10 minutes, I want to say when I was talking about, at the beginning, I was talking about that this cryptography is really protecting the confidentiality of the message. I want to send a secret message, right? So that's basically a lot of time what cryptography is about. But a lot of time people kind of mess up with, get it mixed up with the hashing. Hashing function is actually, we are talking about not to really protect the confidentiality of the message. Sometimes I don't care the message is, encrypted or not, but I want to making sure that you get the same message that I send you. For example, the best example is really the depositing to the bank. If I tell the bank to deposit $200, and the bank will deposit $200, it's very important that they know it's $200 that they know to deposit, not 20, not 2,000. Well, I don't care they deposit 2,000, right? But I want to making sure, or the bank is probably making sure that when you say 200, it is really mean 200. Or I would say that, hey, tomorrow test exam is going to be on chapter 234, and you will say, Professor, are you sure 234? You want to making sure that integrity of the message is right. Or I would say certain, message that you want to making sure that the message that I receive is actually the message that you sent. So that's a different kind of protection on the message than the cryptography that can do. Sometimes you do, sometimes you don't care, but in this case, the hash function is really care about the data integrity instead. So that in cybersecurity viewpoint, this is another cybersecurity objective. We are protecting the integrity instead of the confidentiality of the data. So that's pretty much that's what I said in here. So what hashing function work is like, so with the cryptography, where the encryption and decryption algorithm, or we have to go through. So if I send 10 alphabet, I should get 10 alphabet back, right? If I send 1,224 alphabet, I should get 1,224 alphabet back. So that length of the ciphertext and the plain text has to match, because otherwise I don't know what the message is. It has to be exactly the same length of the message, right? However, in the hash function, it's different. When I send a message, I say, today we'll be talking about this and that, blah, 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 I'm going to send this message. That length could be, I don't know, 1,256 bit of message. But then when you get to go through the hash function, it usually gives you an arbitrary length to a shorter random looking. It's still random looking. That means that, you can tell what is that message about, but it's a shorter length, fixed length message. We call it message digest to making sure that this is actually what the message sent. So it actually used in a lot of, sometimes if you're a software developer, if you're going to develop software, your software code, you got to making sure that what you code, tell the program, your computer to do is the same code that, people see or sometimes. So you're verifying the integrity of the message in here. But it is really, it's not for you to read the message or to get back the original message, because they might not be care whether that's confidential or not message, but what it care is really making sure that the message is the same message that you sent. Okay. So that's that. Yeah.
Oh, I mean, it's just like 7 more minutes. I don't know if you want to jump in
so maybe
topic.
Maybe we'll save that the next time, but let me go really quick. So that's what it talk about, I think I can go through it in 7 minutes, and then we can do a review maybe next time. The hash function usually is like, symbol H, and then so you'll have a message digest, which is a Y, and then you go through this hash function. So this hash function usually have a length of 160 bit or 256 bit, really, really significantly shorter than the original message. So with that, we also need to care about the attacks. Actually, so we don't want to have, maybe we can talk about, so when you exit, usually is your original message, right? So if you have an alternative message, you want to make sure that alternative message, when you go through the hash, it will have a different message digest than your original message. So each message will have a different message digest. So to indicate that the message is not the same. So the attacks will be, there is actually these 3 attacks in here that we need to be careful. And in this hash function, people are constructing this hash function all the time. You know, most famous one is probably SHA-1, SHA-2, and SHA-3 now. They have that, but they basically, you want to making sure that different message will give you a different message digest, like, so to speak, you know, the different 126, 25-bit message in there. So suppose you have a hash function and then turning your, now remember, this is not ciphertext and plain text we're talking about. We're talking about a message and a message digest. A message digest is indicated the integrity of your message. So X is a set of the message that you're going to send. Y is a finite set of possible message digest. X is the message. Y is the message digest. And if you've chosen an X, then compute the Y by applying the hash function on your message. It should be getting a valid pair, right? Your message and your message digest. It should be going hand in hand. If you do have a different message, you should have getting a different message digest in here. So then the first attach we call preimage, and second preimage, and then the collision. And collision is the one that is actually really, you know, a lot of people talk about that. Is your hash function have collision? That's what they usually refer to. But again, you know, your hash function, what mean the preimage is a hash function. You turn a message to a message digest, and then you have a message digest in your hand. And then your goal is to find a message that can actually, such that you can hash that message and you get that message digest. So that means that you do not know what the original message is about. All you have is the message digest. So now, can you do the message? If you just have the message digest, can you find out the original message that will result in, or that will give you this message digest, right? Go through the hash function. So then that can trick the person, right? Okay, by the way, you know, this is the message digest, and you can send a message, the original message, to have that message digest in there. So this is like kind of like doing it, so to speak, backward. And then second preimage is like, you will have a message in here. You have a message already. This is what I was talking about, you know, that probably a lot of people worry about. It's like, you have a message, you know what is a message digest will be like, but can you find another message that will actually result into the same message digest in here? So that means that I can trick that person. I can say, hey, your message digest, let's say, for example, it verified the integrity of you saying you're depositing $2,000, right? I can find a different message. I can say I just deposit $20, but it will have the same message digest as I'm depositing $2,000. So you're tricking the system. You're tricking the system that the original message is not the original message, but you're replacing that with whatever message that you want. So when people say, meet me at noon, but you actually send, you know, we'll get you the message digest. And then people say, oh yeah, this is really, you know, the message is really true, hasn't been altered, but you actually alter the message and in have the same message digest. And then people were thinking about that, oh, that must be the same message, that must be the original message, but it's not. So then you can trick them. Instead of attack at dawn, you might tell them attack at midnight instead. So that is no good. And the collision is the one that we really worry about the most. That is like, you will find a tax. This is like second privilege is like, okay, you have a alternate alternate message, and it will give you the same message that I said. In collision, that means that you can find two messages, two different messages, but it will actually give you the same hash, or is the same message digest in here. So then that means that you cannot really confirm the integrity of the message, right? Because like you send two different messages, it will get you the same message digest or same hash, usually a shorter link. And then how are you going to know, which message is which? So a lot of the time that when you're constructing a hash function, collision is the one that people need to worry about the most. Like, I don't know how they actually, test it and stuff and construct it, but a lot of them, they really put them into a rigorous testing and making sure that the hash function does not have these three different, attacks, so to speak. So I think that's concluded my first day of lecturing. So I have 1 minute left for any last minute questions.
Okay. Actually, we have one in the chat room. Does perfect randomness imply absolute security? At least theoretically speaking, ask Javier Cabezas.
So randomness is a very important feature in cryptography. Yes, you need to be random, and this is like lead right into the next lecture talking about probability theory. It's fantastic that you do, but that doesn't guarantee you the absolute security. Nothing can guarantee you absolute security. So just because you have randomness, that means that your system is most likely, as I say, computational secure, right? So it will take people a lot of time to guess, because if you have a random message, random output with your encryption algorithm, people will say, okay, it could be this, it could be that, it could be that, right? So randomness is the key, is really, to invent or in the crypto system, but that does not guarantee you the secure, absolute security.
Good. Any other question? How close can we get to absolute security? Ask Alfredo Millano.
We just can't. Yeah.
Far away or very close?
Except even the one-time pad, the thing is like, we are really smart. We are really smart. Everything you do, there is a way to break it, so to speak. So no, if you're thinking about we can achieve absolute security, you actually fail already. you have to, but let's say you're inventing a new crypto system, you have to think about that some way, sometime, people will break your system. Now, all you need to do is just like making sure that the system is good enough, complex enough. It takes more time, so it can achieve, your goal to sending secret messages. Same thing with cybersecurity, right? I'm working in cryptography, is just one part of the cybersecurity. When you're working on the cybersecurity field, you have a computer network. You do all this like security control, making sure nobody break your system. At the same time, it's just a matter of time, right? You have zero-day attack. You have some vulnerability. You don't even know that people can exploit it. Right, so it's just really a matter of time. People will find new methods. People will find new ways. There's internet. You communicating. The hackers communicating. So you sometimes you actually really expecting people to break your systems. So then that way that you can create a better system. It's really a mouth and catch game. You do it this way, they break it that way. Okay, and then you do it different way, and they break it a different way, and then you just like keep going back and forth. So that's why that is really interesting field. It's really dynamic field. You have job security. You will always have a job, right? You'll be in the cybersecurity field because there's always new way to break things.
Oh, that's very good then. So actually there is a counterattack from Geoffrey Sanchez. He said perfect security is a continuous change of the system then.
Continuous change of the what, student?
The perfect security is a continuous changing of the system.
Yeah, then. Exactly. So exactly, you got right to the point, because like it might be computational secure today, as I say, the computational power is increasing every year, right? And it might not be computationally secure than the 2 years from now. So now that you have to, continuously improve your security on your crypto system. So, yep. And then later on the last day of our lecture, you will see something we call provable security. Still not 100% secure proof. You always need to think about what adversary can do to counterattack, right? You have the counter action. And very same as cybersecurity as well. You always think about. So for example, this is what just came in from my work too. Not from my work, like someone was talking about, like, how your phone can do your fingerprints or your face, reading your face, face recognition, and instead of a password putting in, they say that you always assume that people will break, your system, people will get your credential to get to your account. With fingerprint and facial recognition, you cannot change your fingerprints, you cannot change your facial recognition. That means that if people get data, they will break into your system for sure. So you should actually avoid using biometrics, as a password. You always use a password, because if people break in using your password, actually they can break in without using your password, but that's another story. But if you break in using your password, you can always change your password, right? So that's why sometimes your account needs to be
that's
like,
a nice starting point.
Yeah,
Wow.
this is like the point. You have to be careful, because like you have to assume people can get your data. You have to assume people will find all kind of way to break into your system. So now how are you going to protect yourself, right? And then
So
you
people
think
can
about
get
this
data of the my fingerprint,
Yeah. Think about it.
digitalization.
Your fingerprint data is somewhere on the system. If people can get it, they get it everywhere. They can get into all your system, your bank account, your cell phone, everything.
That's
Same
amazing,
thing with facial
because
recognition.
people used to assume that, biometric information is going to be
It's more
unbreakable.
secure. Yeah, no, it's not unbreakable, but your data is somewhere on the system, on the computer. So it's just a matter of time. People will get it. It might be secure for maybe 10 years. I don't know, 5 years, if we cannot figure out a way to get it.
I get the point.
Yeah.
Wow.
So it's really to the point, no system, is really 100% secure, that we will always playing this game, getting better and better. And then, and people will always find a way to break it.
That surprised me. So surprised me a lot. Okay, we have a final question from Xavier Cabezas. Hash function sounds good, but how difficult is to build a good one?
Yes, it's very difficult. So again, collision is the one that you need to worry about the most, right? I cannot afford to have 2 different messages to give me a same message digest to verifying that is that message. So when you construct a hash function, you have to, it can be constructed. People can invent hash function all the time, to, as I say, I think SHA-1 and SHA-2 is not really secure anymore, and SHA-3, and that's also MD5, MD4, MD5. And then they are always evolving, because they're cracking it, they break it, so to speak, and then they have to improve their function and stuff. But the point to introduce hashing function to you guys is to show that this is actually protecting the integrity of the data. A lot of the people thinking about hash function is cryptography, which is not true. So I just want to make sure that now that you have this lecture, you should know the differences, and then you won't be mixing up these 2 things together. It's the most common mistake, a lot of people.
Okay. Oh, thank you, Jennifer. I want to add, I have a final question, but in the meantime that you responded, I'm going to change the screen, because I need to take a picture.
Let me stop sharing then.
Yeah, and actually I saw in your LinkedIn post, I think it was yesterday, that you were celebrating that you get certificated with the quantum computer.
Yes.
Quantum computing.
Yes. That's why we will be talking about the last lecture. I will introduce quantum computing and quantum cryptography a little bit, because that is something that I've done before.
Yes, and then you say that it's a threat. I mean, there is new challenges from the cybersecurity. I would like you to give us a very short comment about that, as as a
I will.
Appetizer of what you are gonna give us later on.
Oh, right now?
Yes, but just a little comment about why
Oh.
do you think it's gonna be?
Yeah, so that's kind of actually twofold. So when we have quantum computer, because it can really speed up the algorithm, right? So remember when I talk about the computational security, it might take 4 years to break the code, but with the quantum computer, it might take sooner to break the code. So that's why that it's going to be, a problem. So what quantum computer is not doing well is actually parallel processing. So there is a competition. I'll put the link on the lecture notes too for you to talk about. At least in America, there is a what we call a NIST. NIST is a National Institute of Standard, something I don't remember, but it is the institute, American institute, that they provide standards. So they are going to, they already have a challenge for post-quantum cryptography. That means that we are going to, have the crypto system that actually can combat, the quantum computer. You might think that, oh my gosh, quantum computer is so supreme, nobody can break it, but it's not true, because quantum computer is not really good at parallel processing. So that competition is already in progress, and then they are going into the final stage. So they will be, if you look at that, I don't know I haven't been following too much about it, but there is algorithm that going to come out and may perhaps become the standard of the future, because we were really worried about, quantum computing. And we will talk about some of those algorithms as well.
Okay, thank you very much. I really appreciate, Jennifer, for your time to, for your first lecture. And I would like to thank you everyone to assisting. And just as a reminder, the next course starts at 14 hours, at 2 p.m. And we are going to have a Jennifer again on Wednesday, 9 a.m. local time. I think it's 7 a.m. in San Diego time. My apologize to make you like an early bird.
No worries. I hope the lecture is interesting enough, and then to really, help you guys understand there's so much mathematics behind, cryptography, that you really need to be a very good mathematician and computer scientist, to really truly understand this field and protect our nation and our world, from cyber attacks.
Okay, so bye-bye. See you guys on Wednesday.
See you guys on Wednesday. Everybody have a good one. Bye.
Thanks.